So this section is part of a series of lectures or a course on transport in foods as porous media. And in this one, we're going to talk about transport mechanisms. Everyday sponge like this one is a porous medium that we are all familiar with. Most foods can be treated as porous media. So here I just show two examples. First, bread, which is very obvious. It's porous. And then rice grain, which is not that obvious with our naked eye, but high resolution scanning can show the porous structure. We are going to abstract these for the sake of discussion, these porous media. The real ones are so complex, the pores are so tortuous, connected or blocked, but for the sake of discussion, we're going to abstract porous media with this kind of a picture where there is a solid and there are pores. The pores can be filled with liquid or gas. So this is how we're going to abstract, and we're going to use this picture again and again. So now we're going to talk about how water moves in porous media due to various driving forces. And we'll talk about three common driving forces. One is applied pressure, one is gravity, and one is capillary pressure.
And now we can have applied pressure. What is applied pressure? So we got more water in the sponge. And so if I have a column of water on it, that will push water through the holes of the sponge, and that will cause a flow of water through this porous media. Another one is we could have like a air pressure, just air pushes out the water through this. So it can be hydrostatic pressure or it can be pneumatic, but it can also be this squeezing, so mechanical pressure. So mechanical pressure can squeeze the water out, meaning mechanical pressures can cause, the squeezing pressure can also cause flow.
Okay, so now we look at the other driving force, gravity.
And so when it's completely soaked, as I take it out, you notice water drips out by itself. It doesn't need anything. That's because gravity is acting on it, and gravity is all that is needed for water to be coming out of the sponge. Now, this process will stop. It will not stop when all the water drains out. It will stop at the point where the force of gravity is just equal to the attractive forces that there is, which I'm going to talk about in a second. So this was my gravity. As you can see, it is starting to.
Okay. And now, finally, we talk about capillary pressure.
And I'm going to touch it to the water. And so before, water was coming out of the sponge. But now, as you can see, water is coming up. It's not coming out, it's coming in. It's actually, water is getting attracted. So there's attraction between the sponge molecules and water, and it's pulling water into the sponge. So if we think of the last two, the gravity and the mechanical forces pushing water out as being positive forces, then this one, the water is experiencing a negative force. It's actually just being pulled into the sponge. And so then this one is because of the attractive forces, and capillarity is one of the attractive forces. So this one is a negative force that's causing flow of water into the sponge.
So these different driving forces contribute to the flow of liquid in porous media. And in the next slide, we're going to see some of these forces in a food context. So like the sponge, water in food can also move due to various mechanisms or various driving forces. Let's look at some of them now. So water can move by gas pressure that we are familiar with. For example, how an egg might explode in a microwave oven, or how the bread rises during baking. So there are gas pressures that are generated. Then capillary pressure is also something we are familiar with. We may not see it all the time, but this is how a material dries. This is how water comes from inside of the food to the surface. Then swelling pressure is again something we kind of know, but we don't think about it that way. So let's say when the beans are soaked, they swell, and that would produce a pressure. So in this case, meat cooking also has similar effects or driving forces. As the meat is heated, it can hold less and less water and it shrinks. So there is going to be a shrinkage associated with the amount of water that there is, and this is handled using swelling pressure. And finally, there is the gravity that is true for very wet material, that gravity can cause water to flow in a food. It is hard to think of one particular food product or processing where we have all of these, but we have one or more of these in most processes, and when we try to analyze the food process, we'll just pick the ones that are most important. So that was liquid. Now, the ways vapor can move inside the porous medium is shown here using cartoons. First of all, on the left, in the pore spaces where you have gases, like vapor being one of the gases inside air, vapor would diffuse through, and this is molecular diffusion. This would be binary diffusion of vapor in air. So that's one way vapor can move inside the porous medium. The other one would be just flow. So inside the porous medium where you have vapor and air, because of pressure gradients in the porous medium, the vapor and air together can simply flow, and that would be the other mechanism for flow of gases or vapor in the porous medium. Later, we will set up flux for vapor. So when we set up for the flux, then we have to say that the total flux is equal to that due to molecular diffusion and due to flow. So now we come to how heat moves inside porous media, or heat transports inside the porous media. What are the mechanisms? So we notice that in the porous medium we have solid and then fluid and gas. So this is my solid and water and gas, and there's going to be heat conduction through each one of them. And so to include conduction, we have to include conduction through each one of these phases: solid, water, vapor, and air. So that's how we will set up the conductive fluxes. Then on the right, we look at the the contribution to the heat due to flowing of the fluid or the gas. So there we have water and gas, and then each one, as they flow, then they're carrying heat, and that has to be considered. So you notice also that as the fluid transports, it's not just the bulk flow. There's always diffusion like movement also, like capillarity for water, or like the binary diffusion for vapor. So the total movement due to flow and diffusion needs to be considered in what the amount of heat is being convected. And so later we're going to set up the fluxes that will include the heat fluxes that will include this conduction part as well as the heat movement due to flow. So all of these mechanisms for fluid transport and heat transport can be grouped into two basic types: diffusion or diffusion-like and convection. By grouping them into these two, it will help us in writing the flux expressions. So let's look at, for each component that we have, what is their diffusion like and what is it like flow. So for water, diffusion like movements would come from capillarity or from swelling pressure related or swelling pressure driven diffusion. So, and the flow of water would be due to gas pressure, or if it's very, very wet material, it could be due to gravity. So that's for water only. Now we look at vapor. So in vapor, diffusion-like movement would be the molecular diffusion, and flow would be due to gas pressure. And finally, for heat, diffusion-like movement would be the heat conduction, a transport of energy, and then the flow would be due to the heat carried by the fluid flow. So the flowing contribution in heat would be due to the flowing fluids. Okay, so what I would like you to see, that there's only two kinds that we are putting all the mechanisms and fluxes. One is diffusive type flux, and the other is convection or flow related flux. We're going to use it when we set up the flux expressions. The two types of fluxes that we just mentioned, we're now going to talk about the diffusive or diffusive type flux. And we are also going to restrict ourselves to the very simple two-component system and not get into porous media yet. We just postpone porous media to the next slide. So for heat, the diffusive type flux, as you all know already, as heat moves from hot side to the cold, the heat flux, which is the amount of thermal energy that transports due to heat conduction in watts per meter square, is given by this thermal conductivity times the temperature gradient, of course, with a negative sign to keep it thermodynamically consistent. And so this is for heat conduction, and for mass diffusion, we have this diagram where these red molecules, so we're trying to show mass diffusion in a gas. So these red molecules, let's say, are of a different type. And if the diffusion gets started, then the reds are going to mix. Remember, they're moving randomly, but even though they're moving randomly, if you think of an imaginary line, more reds will go that direction than the other direction, even though they're moving randomly. So net result would be things going in this direction from where there is more to where there is less. And this is given by the good old Fick's law of mass diffusion, and the mass flux, just like the heat flux, is in kilograms per meter square per second, or in molar units, kilomole per meter square per second. And in a very analogous way, that's equal to diffusivity of the component A, so A being the red and B being the blue, diffusivity of A in B and the concentration gradient of A with the respective units that are also similar to those in the heat side. If we rewrite the heat equation as K over rho Cp times del rho Cpt del X, then this quantity is joules per meter cube. Just like here, it's kilomoles per meter cube or kg per meter cube. So very analogous. And then this would be the thermal diffusivity that has the same unit as mass diffusivity, which is meter square per second. So this was a recap. Most of you know this already, but this is for simple two-component system. Now we're going to extend this to porous medium. We're going to now extend those diffusive flux laws that we just saw into a porous media. Those were shown for simple two-component system, but now we are extending to multi-phase, multi-component porous media situation. But we do this extension in kind of ad hoc way, even though there's theory behind and it has been shown that this is very possible. We're not going to get into those theories. And so the two laws, one is for heat conduction shown here, and the other is for mass diffusion, where it goes from higher to lower concentration, a mass diffusion Fick's law. These are extended to porous media by what's called averaging. So they're averaged over some small representative elementary volume that is discussed in other places in this series of lectures, but they are averaged over the quantities are all averaged over this representative elementary volume. So in case of heat flux in a porous medium like this, then we're going to have K thermal conductivity that is averaged over the phases, solid, liquid, gas. It's going to be some sort of an average, and we'll talk about it later. Likewise, temperature is also averaged over a representative elementary volume. And in the same analogous way, diffusivity, here we're talking about if it is molecular diffusion, it's of course through the pores, but it's averaged over a representative elementary volume. If we are talking capillary diffusion, the same idea. And then the concentration, whatever concentration we're talking about, is also averaged over a representative elementary volume. So of the two types of fluxes that we had mentioned, diffusive type and convective, we just finished diffusive, and this one we're going to talk about the convective flux. To do that, we're not going to start with porous media, but a simple system where we have these yellow particles moving in a clear fluid, and we're going to try to define the flux. So these yellow particles, let me play the video for a second. So these yellow particles are being carried by the fluid. So let's say the fluid has a velocity u at this location. At this location, let's say the average velocity is u. Okay, so with that velocity u, the flux, the mass flux is given by, at this point location, let's say, is given by u times c. So how much is there times the velocity? C is the concentration of the yellow components. That gives the flux in kilograms per meter square per second. So likewise, and if we look at the units work out. So velocity is meters per second and C is kilograms per meter cube. So this will give me kg per meter square per second as shown here. Okay. So in a very analogous way, we can talk about heat flux due to flow. So this was mass flux due to flow, and this is now heat flux due to flow, and that is joules per meter square per second is the velocity times, just like here we had the mass content, here we have the heat content, which is joules per meter cube, rho times Cp times T. So joules per meter cube, that gives us joules per meter square per second. Now we extend those convective fluxes to porous media. So the velocity in a porous medium is really averaged over the entire surface. So this u, the velocity is really a velocity averaged over the entire surface. So with that velocity, the mass flux is going to be defined this way. Mass flux is velocity times how much is there, which is rho in kg per meter cube. Note that this is density and not concentration like in the past. Why? Because this u as meter per second, the way u is defined in porous media, this u in meter per second, let's say we're doing this for water, so flux of water. Okay, so then u is meter cube of water per meter square per second. So that's this meter square cancels meter cube and we get meter. That's the meter that we have. So you see it is meter cube of water. So then when we multiply, it works out if we use density of water in kilograms per meter cube. So when we multiply again, we get flux of water, mass flux of water this way, kg per meter square per second. In an analogous way, heat flux due to flow would be joules per meter square per second, and it will be this velocity times the heat content. Now notice that it's a multi-phase flow situation. So it's not just water. So this heat flux due to flow would have to be done for each phase of water, vapor, air, and added together. So the equation written here is really just for one phase. Since we divided all the fluxes into two types, diffusive types and the convective types due to flow, then the total flux would be diffusive flux plus the flux due to bulk flow. So in this animation here, we have diffusion now, and now that would be given by our Fick's law type equation, and then on top of diffusion you can have flow. So notice that the diffusion didn't stop when there is bulk flow. So the bulk flow is on top of the diffusion, and the total mass flux is given by the summation of the two, and here they are in terms of units. So they both, each component have the unit of kg per meter square per second, or mass per unit area per unit time. So this is still not in porous media. This is still in simple two-component system. And now if we extend this to heat in a very, very analogous way, so we have conductive flux, okay, and then the convective flux that is due to the flow with the velocity u and the energy content being rho cpt. Again, if we look at the units, they will work out because the unit for this, for example, u is meter per second and rho cpt is joules per meter cube. Now this one, it doesn't follow exactly, but if we rewrite the equation this way, minus k over rho cp times del x of rho cpt, then the units for this would be meter square per second, and units for this is joules per meter cube, and unit for this is meter. So they're exactly analogous. And now we're going to just extend these for the porous media. So now we extend that equation for total flux in a simple two-component system that includes diffusive and convective type. We're just going to extend that to porous media by writing the terms for each phase, or noting that we need to write them for each phase. So then the mass flux, diffusive plus convective, is written for water, vapor, air. So we're going to have these three mass fluxes. Likewise, the heat flux is going to have, for the convection part, it's going to have water, vapor, air. And for the conduction part, we're going to have conductive heat fluxes in all four. So we're going to basically use these equations for each phase, and that's how we're going to build the flux equation for all the components together in the overall heat equation or the mass equation for each phase. This we will be developing in the following section.